So we have seen the structure of a simple RNN in the previous video, but how does backpropagation work now? So the backpropagation that is used in training RNNs is called backprop over time. I'll explain this. It's actually not a very hard concept. Since we know backprop very well, backprop over time is basically a careful modification of this. Okay, so let's draw a diagram first, right? You have our xi1 here, right? Or x11. And of course, the inputs to this is O0. O0 is mostly zeros or some random value, right? Then of course you have your weights here. Remember, okay, I'll draw the weights a little later, right? Then I have my O1 here and my xi2 here, and all these are my functions, f's. All these are my f's, right? This is my activation units, bunch of activation units, not just one, right? Here I get my O2. This is my xi3, right? Let's assume my O4, so on and so forth. Let's assume finally I have, let's just assume, okay, but I have O9 here, xi9, which gets O8 as input. This is the same function f, and it generates O9. And I have one more layer which takes xi10, right? And this same function, it generates, let's say, O10, right? So let's assume my xi is xi1, xi2, so on, xi10, right? And of course my O10, I will take it up here, right? And I have a softmax layer which creates my yi hat, right? Let's look at all the weights that I have. I have weight w here, the same weight at different time step, weight, same weight. I have my w dash here, same w dash, just repeating itself, and my w double dash here. Okay, and this is my time axis. Let's not forget that. This is my time axis. Lot of people, when I draw this diagram, even some students, even sometimes a lot of people who are very well versed with neural networks, they get confused and they think this is one layer after other layer. No, this is just time axis. This is just one layer repeating itself over time. Okay. Now when I have my yi, look at this. When I have my yi here, I have a loss function also, which takes yi and yi hat. If I have a simple problem like this, our example problem is what? Is a binary classification problem. Okay, so I can just use a log loss type of simple binary log loss. Simple binary log loss. Now let's look at the calculus part of it. Okay, now just to be clear, my O1 is f of, my O1 is f of w into xi1 plus w dash into O0. Okay, similarly my O2 is f of, my O2 is f of w into xi2, w into xi2 plus w dash into O1, so on and so forth, right? Similarly my O10 is f of w into xi10 plus w dash O9, and my yi hat here, remember my yi hat is some g, let's call this softmax function g. Okay, just for simplicity, okay, because this function might change. So it is g of, right, it is g of w with two dashes multiplied by O10, right? I have my O10 here and I'm multiplying with w double dash, right? Simple. Now how does the calculus work here? So let's look at the forward prop. First let's look at the forward prop, then we'll look at the back prop. Very simple notation, very simply, to understand this very easily, the direction of your arrows or the forward direction in time is the way your forward propagation works. Your forward propagation literally works like this. What I've written here is your forward propagation, right? What I've written here, the sequence of steps. First you compute O1, then you compute O2, then you compute O3, so on and so forth. That's your forward prop. And while you're performing your forward prop, your weight W and W dash are all, W's and W dash and W double dash are the same. They don't change, right? Weights only change in the back prop. So forward prop, just use the direction of arrows. The direction of arrows. That's why this notation of representing RNNs is very powerful. You can just follow the direction of arrows to write your forward propagation equations. These are your forward propagation equations. This is how it happens. At time step 1, this happens. At time step 2, this happens. So on and so forth. Time step 10 and time step 11, you get the class label that you want. Okay, once you get the class label, you have your loss function. Now what about the backward prop? Forward prop is the forward direction of arrows. Now what about backward prop? Okay, let me write it down here. I want to use the same page here. My backward prop is the opposite direction of your arrows. The opposite direction. The opposite direction of your arrows. Actually very, very simple, right? So let's look at it. So you have your loss function here. So I can compute the derivative of this loss function with respect to yi hat, right? So the first thing I'll do is derivative of loss function with respect to yi hat, right? Now, if I get this, I can compute the derivative of my loss function with respect to my output 10 also. The derivative of my loss function with respect to output 10 is nothing but the derivative of my loss function with respect to yi hat multiplied by the derivative of my yi hat with respect to O10, right? Because look at this, my yi hat depends on my O10, right? It depends on O10. So I can compute the derivative of this with respect to O10 by just chain rule. Right? Similarly, I'll just erase this. So very straightforward, just following the forward arrows, right? I'll just erase this so that I can use this space, so that I can explain all of this in a single page, right? So now what I'll do here is, what is a, how do I, now I want to modify my W double dashes, W2 dash, right? So how do I do this? My derivative of loss function with respect to W2 dash is equal to derivative of my loss function. Look at it, let's work backwards. The first one, derivative of my loss function with respect to yi hat, and my yi hat depends on both O10 and W double dash, right? So my derivative of yi hat with respect to my derivative of yi hat with respect to W double dash. I can compute this easily, right? Because look at this. What is this? My yi hat is basically function g. This is standard. This is very simple. I'm applying a function g on top of the dot product of both of them. So I can easily compute this, right? Straightforward. So this is simple. W double dash is simple. Now let's look at W's and W's, W's and W dash. Okay, now let's look at derivative of L with respect to W, this W, that's what I mean, right? Because this is happening over time, right? First I'll edit this W, right? The same W, I'll edit it again here. So eventually I'll just get one W. So this is called back propagation over time, because remember, this is the time axis. So I'm back propagating over time. That's why RNN back propagation is called back propagation over time, because this is the forward in time, right? This is the forward step in time. So the backward also will be in time. Just reverse the arrows. Okay, this W, the derivative with respect to this W will be derivative of L with respect to yi hat, and your yi hat now depends on O10. So multiplied by derivative of yi hat with respect to derivative of O10. Your O10 depends on W. So derivative of O10 with respect to W. That's it. So now you modify this W. Similarly, you can write it for W dash also, right? So first you modify. Again, look at this. When we are going forward, we went in the direction of arrows. While we are coming back, we will come in the exact opposite direction. So first we'll modify these W's. Then whatever is the modification, we are tracking back over time. So this is called backprop over time. Very, very simple concept, right? So, but what is your core neuron? Because this is over time, what you literally have is basically only one weight and two weights and three weights. You literally have only three matrices in your memory. First you modify this based on the derivatives that you get here. Then you modify the same thing again with respect to the next step, so on and so forth. So at the end of it, you'll reach here. At the end of it, you'll reach here, right? When you reach here, you have modified or you have back propagated your weights and you have updated all these three matrices with respect to only one data point x1 and y1. So till now you have only processed one data point, right? Because your xi, you've only taken one data point, which is xi, yi. Now you repeat it with the next data point, so on and so forth, right? So your back propagation is happening over time. There is a problem with this, right? It's very simple. The simplest way to remember this is to follow the direction of arrows. If you follow the direction of arrows, you get forward prop. If you follow the direction of arrows backwards, you get backward prop. But the backward prop happens over time. These are not different W's. A lot of people get confused. I used to get confused when I first learned RNNs. This is the same W. Everything's happening over time. It's not multiple layers. It's just one layer. Okay? Having said that, I've repeated that concept multiple times because I don't want you to get confused with that. That's the reason. There is one problem with this. Look at this weight that you'll modify here. Look at the weight that you'll modify at the last time step. Look at this. You have 10 words here. You have 10 words here, right? So your derivative of L with respect to this W, right, is a product of lots of other partial derivatives, because you have to follow this whole path. You have to follow this whole path backwards. So when you come to the end of it, when you're back propagating, when you come to the first word, this weight that you have to modify for the first word, what happens there is basically you run, because your derivative with respect to the weights in the first layer with respect to the first word, right? This is the derivative with respect to the first word. This has lots of multiplications, it has lots of multiplications of other partial derivatives, If you recall our chapter, our MLP chapter, we realized that when you have lots of these multiplications and most of these values are less than 1, or all of them are less than 1 actually, you can easily run into a vanishing gradient problem. You're running into a vanishing gradient problem not because you have many layers, but you're repeating this operation. Over time. Imagine if you have a sentence, let's assume you have a sentence which has, let's say, 100 words. You have a sentence that has 100 words. So you literally have 100 multiplications of partial derivatives, right? And if your activation unit, let's assume your activation function, f, is, let's say, sigmoid or tan h. Let's assume it's sigmoid or tan h. Then all the derivatives are less than 1. When you multiply it, the vanishing gradient problem kicks in very, very fast. Right? You can also have exploding gradient problem. If at the end of the day you're multiplying lots of partial derivatives, if they're less than 1, you have vanishing gradient. If they're greater than 1, so all your partial derivatives, or at least some of them, are greater than 1. Then you'll run into the exploding gradient problem. And please note that you're not running into this problem because you have lots of layers. You're running into it because you're performing back propagation and forward propagation over time. Similarly, you're performing forward propagation over time. This is happening. The vanishing gradient or the exploding gradient problem you're encountering not because you have many layers, but because your sequences are long and you input one word in the sequence after the other. That's the problem. We will see how to, of course, there are special, this problem has been a major issue for RNNs for a long time, but there are modifications to the simple RNN. So what we have seen till now is a very, very simple RNN. There are modifications to simple RNNs called LSTMs and GRUs. These are special RNNs which will avoid the vanishing gradient problem or the exploding gradient problem a lot, right? So there are ways around it. So these structures are super important. These are special purpose. These are specialized RNNs. We'll see that they're far more complex than this, but it's not too complex that you can't understand. But these are special purpose recurrent units. Okay, what you have here is one recurrent unit, right? What is your recurrent unit? Your recurrent unit is simply this. Your recurrent unit is simply this. You have your yi and you have your xi here. This is your recurrent unit. Right? There are special purpose recurrent units called LSTMs and GRUs, which can avoid most of the problems of vanishing gradients and exploding gradients. Right? So we'll come there. We'll come there when the time comes, after we learn some more concepts.